Welcome to Math 31. This is the second part of the lesson on differential equations, and I'm going to concentrate on motion problems, which are a very, very common application. And the questions will look very similar to what you were dealing with before in derivatives, but you will, as you get into them, you'll see that there's a slight difference. So, as you know, v, the velocity function, is the derivative of the position function. And as well, the acceleration function is the derivative of the velocity function, which is the second derivative of the position function. So we know all that. But the difference is now in that instead of going from the distance function and working our way up to the acceleration, we'll be going the other direction. And in fact, this makes a type of sense because particularly with vertical questions, those of you taking some physics, you'd know that the acceleration due to gravity is 9.81 meters per second squared, or negative 9.81 meters per second squared. And we know that. So, in fact, you are typically given the acceleration function, and you then work backwards to find position and velocity. So those of you who've spent some time dealing with kinematics will know that that's how that works, and that's how you, in fact, derive those kinematic formulas. But anyways, let's take a look at a question and then go on from there. So this is the kind of an interesting one because the velocity function is given as a trigonometric function. Which seems a little odd. You wonder what sort of driving pattern this guy's got. Now this is starting at t is equal to 0. Okay, fair enough. And then we want to find out how far the car is going in 30 minutes. Now, right away, at least hopefully, you'll see that there's we do have the problem of which direction we're going. And you can see right off, I hope, that we're going to have to get the antiderivative. Helps because this is also the antiderivative unit. But even if you saw this on a final exam, you want to make that connection. So we can take this velocity function and recognize that v at t is equal to the derivative of the position function, which is equal to this, 30 plus 20 sine 10 pi t, and then get s at t. So this becomes 30t. Now be careful with this one because the antiderivative of sine is actually negative cos. And what's more, it has to be negative 1 over 10 pi. The k value, which is then multiplied by the 20 that is already there, and then times the cosine of 10 pi t. And of course plus c. So when we mop this one up, clean it up a little bit, we'll get 30t minus 20 over 10, it would be 2 over pi, and then cosine of 10 pi t plus c. Now the thing of it is, what we were trained to do in the earlier questions was look for initial conditions. So we want there to be some information about this position function so that we can solve for the c value. And there is none. All we have is that it's starting at t is equal to 0, but we don't know what the position is at t is equal to 0. Now you might assume that it's 0. And in fact, if you did it carefully, it would still work out. But I'm going to play it safe. And I'm going to get around the little problem by noting that really what we want is how far it went in the first 30 minutes. Now 30 minutes in terms of hours, which is what the units we have, is 1/2. So really what we want is s at 1/2, its position after half an hour, minus its position at t is equal to 0. So what's going to happen when we go further with this is the c value is going to cancel out because we're going to subtract it away. So we got lucky with this one. So s at 1/2, so we go into the formula and I'll write this out again, s at 1/2 minus s at 0. This is going to become, with big old brackets, 30 times 1/2, so replacing the t with 1/2, minus 2 over pi times the cosine of 10 pi times 1/2 plus c. And then take away 30 times 0 minus 2 over pi multiplied by the cos of 10 pi times 0 plus c. Now you can do this a number of ways. Some of you will clean up the brackets. I'm just going to play it very straight, and I'll go 15, clean this up as much as I can all the way down. 2 over pi times the cos of 5 pi divided by 2 plus c minus, well, that's going to be 0 minus 2 over pi times the cosine of 0 plus c. Going even further, 15. Now be really careful. Cos of 5 pi, if you take a look at it, your calculator will give it to you right away. But 5 pi, here's 2 pi, here's 4 pi, and that's one more. So it's actually the same as pi. It's coterminal to cosine of pi, so that's negative 1. So this becomes 15 minus 2 pi times negative 1 becomes 15 plus 2 over pi, excuse me. And then plus c. And then minus, well, cosine of 0 is 1. So this becomes negative 2 over pi, stays the same, plus c. Now I'm going to clean up the brackets, so 15 plus 2 over pi plus c, plus 2 over pi minus c. C's go away, which they have to do, and then we get 15. Now 2 over pi plus 2 over pi is 4 over pi. So the answer then is going to be the car has, boy, writing is bad, has gone 15 plus 4 over pi kilometers. So that's how these things work. That's a plus. Pretty routine, just got to be careful, particularly if there's trig involved. Now let's go on to the next one. These are probably more normal questions because they're given vertical up and down ones. We've done lots of these before, just the different direction. So we got this rocket being fired vertically upwards, okay. Its fuel is exhausted, it has a specific velocity, and then it reaches this height and has reached this height. Now you got to be careful because what it really means is it's okay, at that point the fuel is gone, so the upward force has ended. And as soon as that happens, the only force that's acting on it is the force due to gravity. Now I've got this to 1 decimal instead of the 9.81, which most of you are more familiar with. Still okay. Neglect the effects of air resistance. So we want to find out how long will the rocket continue to rise after the fuel has exhausted. So we don't have a net force issue anymore. We've just got the force due to gravity. Now where you start with these almost always is working with the acceleration. The acceleration is equal to negative 9.8. And as a result, and that is meters per second squared, as a result, if we want to get the velocity function, we note that the v prime, the derivative of the velocity function, must be equal to negative 9.8. So if we take the antiderivative of the velocity of that function, the acceleration function, we'll get v at t is equal to negative 9.8 t and then plus c. Now that's not good enough for us because we're going to need to find out what C is. And I'm going to call this C1. Don't have to do that, but we're eventually going to make our way down to the position function, so I want to keep my C's clear. So initial conditions are what it's all about now. And luckily we have a way to find initial conditions. Because t is equal to 0 occurs when fuel is exhausted. This is when the event begins. So given that, if t is equal to 0 when the fuel is exhausted, then it means that its velocity at that exact instant is 30 meters per second. And those are our initial conditions. So we plug in 30 for the v, we plug in 0 for the t, and as a result, C1 is just going to be equal to 30. So this tells me that v at t, the function itself, is negative 9.8 t plus 30. And the next part of the question is recognizing that this thing, we're trying to find out how long it's going to continue to rise. So you figure out quickly that it rises until the velocity is equal to 0. So that's when it stops. So I'm going to get a little more space to work on this, but that's a start. So now, to finish the question, we take a look at our v function, and 0 is equal to negative 9.8 t plus 30, and then solve away. So 9.8 t is equal to 30, and then just divide the whole thing out. And you were asked to take this to the nearest tenth. So 30 divided by 9.8 will give you 3.06. So t is equal to 3.06 seconds. So it rises for 3.1 seconds after the fuel is gone. Now for the next part of the question, find the maximum height attained. Now, we here have to note that it's a distance, a position question. So this means that we have to get the next derivative, or excuse me, the next antiderivative. So we know that the velocity function looks like this. And that happens to be equal to the derivative of the position function and equal to negative 9.8 t plus 30. So the position function, well, we get t squared, and we divide by 2, and we're going to get negative 4.9. And then plus, well, 30t, plus, let's call this C2. And now we need to get that C2. So we're looking for initial conditions. And if you go back to the original question, at t is equal to 0, the position is 80 meters, height of 80 meters. So therefore, s at 0 is equal to 80. So that gives us enough. 80 is equal to negative 4.9 t squared plus 30, oops, this is 0 squared, that'll make life easier, 30 times 0 plus C2. And then our C2 is going to be equal to 80. So the position function looks like this. S at t is equal to negative 4.9 t squared plus 30t plus 80. And we want s at 3.1. So its position when it's at maximum height. So negative 4.9 times 3.1 squared plus 30 times 3.1 plus 80. Now what I'm going to do is keep that original number on my calculator, that 3.06. So I'm going to square it times negative 4.9 plus 30 times that number, 3.06, plus 80. And I'll get 125.9 meters. So its maximum height is 125.9 meters. Now the next question is when will the rocket strike the ground? Now I know many of you are thinking, I'm just going to use kinematics for these, but I really encourage you to use the calculus just as much as you can to get familiar with it. But the kinematic formulas from physics will answer pretty much every question you need for this type. It doesn't work well when you're dealing with the trig ones. But if the acceleration is constant, then this is a great method. So what we do now for this one, you recognize that when the rocket hits the ground, you're really asking yourself, when is the position s at t equal to 0? So 0 is equal to negative 4.9 t squared plus 30t plus 80. And this will require the quad formula or a graphical solution. So I'm going to use the quadratic formula. So x is equal to negative b plus or minus the root of b squared minus 4ac all over top of 2a. So x is equal to negative 30 plus or minus the root of 30 squared minus 4 times a, which is negative 4.9, times c, which is 80, all over top of 2 times negative 4.9. Now, to be honest with you, I usually will make the leading term positive just for ease and bring it to the other side and change the signs, but no big deal. I'm okay with this. In the radical, 30 squared, the two negatives cancel, so it's plus 4 times 4.9 times 80, 2468. So really this becomes x is equal to negative 30 plus or minus the root of 2468, and then the denominator is negative 9.8. So we go through this one, negative 30 plus the square root of 2468 is equal to this 19.97 divided by negative 9.8. So the one answer we get is x is equal to negative 2.0. And then the other one is based on negative 30 minus the square root of 2468, close, enter, divided by negative 9.8. In doing that, you end up getting 8.13, which I guess to the nearest tenth would be 8.1. So x equal 8.1. And that's the one we want to keep, so we have to reject this one. Time equals 0 is where the whole thing starts. So we can then say it strikes the ground 8.1 seconds after. seconds after the fuel is gone. Now I'm going to do one more question. This is not as long a one, but it does have some interesting angles to it, and then we should be done. So for whatever reason, this woman is throwing a ball vertically upwards from ground level so that exactly 4 seconds elapse before the ball strikes the ground. Now I am making an assumption here that she's actually, when I say ground level, it means her hand is ground level. Now that's an awkward way to throw a ball, but we're treating her release point as being the ground level. So in fact, if you weren't comfortable with that, you knew how tall she was or what her release point was, you could certainly add that height on afterwards and deal with it just fine. So it's not really a big deal, but for our sake, I'm going to say that this is leaving her hand at that point. And the first question is the maximum height the ball reaches. Now, we start with the same way, and by the way, feel free to pause me and go through it yourself. A is equal to negative 9.8 meters per second squared, and I'm taking this to the nearest tenth. So here we go again. V at t must be equal to negative 9.8 t plus c. But the problem is this initial condition. And the way that this one is best done is to remember that halfway, so these things are perfectly symmetric. So if it's thrown from the ground, she throws it up, she throws it down, and halfway is going to be 2 seconds afterwards. So it means that the velocity at 2 seconds is equal to 0. So that's very helpful because we do know that at that point the speed must be 0. And this is, we can use this obviously because that's going to be initial conditions. So now we go on with this. The velocity is equal to 0, and that's equal to negative 9.8 when time is 2. Plus c. And then we can solve this one pretty nicely. Negative 9.8 times 2 will give us 19.6. So that comes to the other side. 19.6 is equal to c. So therefore, the velocity function, v at t, is equal to negative 9.8 t plus 19.6. And now that is not, of course, the maximum height, far from it. But we can keep going through this question. We need to now find, of course, s at t in order to make any headway with this one. So s at t will be the antiderivative of this one. So t squared and negative 4.9 t squared, 9.8 divided by 2, plus 19.6 t, and then plus c. And here we go back to the information that was given to get initial conditions, and it says that it strikes the ground 4 seconds afterwards. So this means, or this tells me that s at 4 is equal to 0. So these initial conditions would allow us to go 0 is equal to negative 4.9 times t, which is 4 squared, plus 19.6 times 4 plus c. And then we work all this one out, and we get the shock of our life. Negative 4.9 times 4 squared plus 19.6 times 4 just equal to 0. So c is equal to 0. Now, if you reason your way through this, this is going to make sense because the position at time is equal to 0 should be equal to 0 if we stick to what we said earlier, that it's being tossed from shoe height. So it means our formula, though, is negative 4.9 t squared plus 19.6 t. And what the question is asking for is its maximum height. So we know that this is happening at 2 seconds, so find s at 2. So we just punch that right through. So S at 2 is equal to negative 4.9 times 2 squared plus 19.6 times 2. 90.6 times 2, I guess. Work all this thing out. S at 2 is equal to 19.6. So its maximum height is 19.6 meters. Let's do the part 2 to this question, which is the velocity with which the ball was thrown. Now, this one is, a reasonable question, but it's not a difficult one. We want to find v at 0. So at time is equal to 0, what is its speed? So you go back. In fact, this would have been a good question to answer first. V at 0, go back to the velocity formula, and that's negative 9.8 times t, which is 0, plus 19.6. So v at 0, when you work it all out, is equal to 19.6. So its initial velocity was 19.6 meters per second upward. So that's the physics teacher in me. I'm putting the direction for velocity. If I was doing this whole question over again, I might well just say find the speed. So that's how we tackle these ones. And the next lesson that we're going to cover is going to go on to, sort of a more formal look at these problems where we introduce the integral to the mix. So a new symbol, a little bit of new notation. So that's it for me, though. Thank you for your time.